we have Dr. Wu presenting. Dr. Wu is an associate professor with tenure in the Department of Health Outcomes and Biomedical Informatics at the University of Florida College of Medicine. He also serves as the director of NLP at UF Clinical and Translational Sciences Institute and OneFlorida Plus Clinical Research Consortium. Dr. Wu's primary research interests include clinical NLP, machine learning, and electronic health record-based drug repurposing. He has worked on various challenging AI topics such as large language models, patient information extraction, NLP-powered computable phenotyping, and disease predictive modeling. He has published over 90 peer-reviewed research papers with over 6,000 citations. His work was supported by funding from the NIH, the Patient-Centered Outcomes Research Institute, and the Advanced Research Projects Agency for Health. Once again, thank you very much, Dr. Wu, for presenting, and leave it up to you.
All right, thanks for the introduction. It's a great pleasure to present in this seminar. So I am a computer scientist. I got my training from computer science. After graduation, I completed PhD postdoc training at Vanderbilt under my supervisor Hua Xu, who happened to be got his PhD from DBMI at Columbia. So it's a great pleasure to share what I'm doing now to use AI to improve medical discovery and healthcare through artificial intelligence. All right, first, let's see. It works. Okay, first, for disclosure, I only work for University of Florida, so you can trust me when I talk about some of the industry people. I will talk a lot of industry people's name, but you can trust me because I only work for University of Florida. But the only exception is NVIDIA because they have very close relationship with NVIDIA to develop some of the models. So I will be very careful when I talk about NVIDIA. So you can trust me talk about other industry names. All right. I am focused on natural language processing, which is a branch of artificial intelligence. And there's a lot of branch in AI, for example, voice recognition, computer image, computer vision, and robotics. And NLP is a very important branch of artificial intelligence. It's actually at the intersection of AI and linguistics. There used to be another name called computational linguistics. You can tell from those top journals from NLP, still like ACL, still they have the name computational linguistics. Well, AI is actually NLP actually born with AI. One fundamental problem in artificial intelligence is how to determine the intelligent agent have intelligence. For example, machines. How do we determine machine have intelligence? So in the famous Turing test, there was a judge C observing the written language between a machine A and human B. If the judge C cannot differentiate A from B, then we say the machine A have equivalent intelligence with B. This is a famous Turing test. So NLP was used to define AI, and the Turing test is defined using written language. It's not using image. It's not using voice because you back to 1950s. It's impossible to put any image and video on the computer. So the only thing you can do on computer is letters. So that's what NLP is used to define the first generation AI. The concept of AI is quite clear, which is trying to develop intelligent agent, not only speaks like human, moves like human. Basically, we're trying to make a copy of human intelligence on the machines. But in terms of how to achieve AI, there was a lot of arguments going on since 1950s until now. There has been a lot of models proposed in the machine learning branch of AI, which is a branch to enable machines to learn from the real world incrementally gradually we can achieve human level intelligence. There has been hundreds of, if not thousands of models being proposed how to make machine learn from historic data, eventually achieve human level intelligence. For example, some of the models are very simple. To learn the posterior probability inferred from prior probability from data. Or you can follow decision tree branch to achieve the best decision branch, or you find the spot vectors that are very important to find a classification boundary that minimize the structure error. And there has been hundreds of models proposed. A similar thing happens in NLP. We know that deep learning is the current solution for all learning branch of AI. But in NLP, it happened very late after other branch. For example, deep learning achieved success in image a long time ago. In around 2000, we have AI model, deep learning model work with image, but it doesn't work for NLP for a long time until 2011. The first generation model based on convolutional neural network first achieved success on NLP. This is the first research approved that deep learning actually works for NLP. Before that, there's a long time the model works for image. When we borrow them from text, it doesn't work. Most of the time, it doesn't converge because of the sparsity issue of text data. Then after 2011, the next generation, the second generation of deep learning model for NLP based on recurrent neural network, or most specifically the LSTM architecture. This is very popular between 2014 to 2016 and LSTM model. And then when time comes to 2018, it looks like the transformer model eventually unified all the branch of learning branch in AI. It becomes a unified solution for all the AI models, no matter where you're learning. And especially after 2020, when a specific branch of transformer, the encoder-based transformer, eventually demonstrated advanced intelligence in terms of future learning, zero-shot learning, and solve all different questions just using one model. We call it artificial general intelligence. Then this branch immediately goes beyond NLP. It becomes almost a unified solution in the entire AI. So you can find this model in different branch, whether you're doing computer vision, computer image, or computer automatic control. This transform model is still the state-of-the-art model. You can use in this model solve hundreds of thousands of different tasks in just one model. We call it artificial general intelligence. So what happens now is this model eventually occupied all the branch of AI. It has a very deep impact to the entire AI industry or academic, because previously we have several dozens of branch, like people working on text, image, video have their own models, but now there is only one model. They previously have to have dozens of people doing different models, but now they only need to have one people. They can solve different models. So this is the chaos status in either industry and academic in the AI branch. So that's why you probably heard that it's hard to find a job in the AI market because it's very chaos until now. People used to work on different branch like 20 years ago. Now they all merge into this one narrow branch of deep learning or transformer models. Along with the model change, the learning algorithm also changed a lot. Before the deep learning, we started using the fully supervised learning mechanism, where we have to develop one model to handle per task, and the output is fully controlled by the model parameters. The only way you can change the model prediction is to change the parameters. This is called a fully supervised learning model. In that model, you have to develop a different model for different models. For example, you have to develop model 1 to have you drive the car. You develop model 2 to have detect fake dollar bills, and model 3 to detect onset of Alzheimer's disease. So basically, it's a one model per task settings. And during the second phase, we shifted the fully supervised learning a bit to pre-training, fine-tuning phase, where we first fine-tune a model, just learning the distribution of data using language models. And then we, after pre-training the model using large number of texts, usually over billions of tokens, we do something called fine-tuning. We add a specific layer. For example, if you perform regression, you add a regression layer. If you perform classification, you add a classification layer. If you perform AR, you add a CRF layer, and then you fine-tune the model and the layer using a small label data set from humans. This becomes pre-training and fine-tuning. In that case, we unify the pre-trained model, but you still have to add additional layer to fine-tuning. So you still have to deploy one model per task. But eventually, after the GPT model, the decoder-based transform model, we have something called generative AI. In that phase, we're using pre-training prompting learning algorithms. In that learning architecture, we removed the task-specific layer away, so the model will keep unchanged. What we do is we add something called prompts, which is additional information we add into inputs. We're using the prompts, which are often some human readable instructions to instruct the model to perform the task. It was until the generative AI model based on transformer, we are able to use instruction to instruct machine learning models to change the model output, which is not achievable in the previous generation of AI models. So finally, we can achieve this so-called artificial general intelligence. We can use one model, solve thousands of different tasks without changing the models, which is advanced level of AI we never observed in the previous generations of AI models. So this is what's happening in the field of artificial intelligence. And as I said, you can compare the different learning mechanisms. In the fully supervised learning, you develop one model per task. You have to develop 7 models for 7 different NLP tasks. During the second phase, you have the pre-training, fine-tuning. In the pre-training, the model is unified as one pre-trained large language model, like the original BERT. And when you apply the model, different subtasks of NLP, you still have to add a specific layer, fine-tune the model, eventually have to deploy 7 different models for 7 tasks. But at the stage of generative AI model, we unify the model into one. We can apply the model. The model is phrased unchanged. We just use different instructions to instruct the model to solve different tasks, which is finally achieve this one model for our solution of dream in the world of artificial intelligence. There are 2 very important observations from the generative AI. First is future learning. The traditional training is very slow. You have to gradually adjust the model using thousands of samples. The model grows like very slow line in terms of observation if you calculate loss. But during this generative AI, we can use only a minimum number of samples, like 1, 3, 5. You can observe the performance grows very sharply. So for example, using just one sample, you can achieve 50, 60% of the growth in terms of performance, which is not observed in the previous generations. Also, zero-time learning. The model can perform a task without using any data from that task, without any human instructions. This is a very promising observation from the new generation of AI, even though the performance is still low. It's around 30, 40 sometimes. But it's a promising. This is the first time we observed this future learning and zero-time learning for generative models. So this is our previous study to explore this generative AI to solve different tasks just using one model with different instructions. And the current game of AI is like Game of Thrones or IT Giants. It's dominated by a law called scale-up law. Under this law, what happens is it looks like there is nothing can't be solved by developing transformer blocks. If 1 million blocks doesn't work, you build 1 trillion, 10 million blocks. If 10 million doesn't work, you can build trillions of blocks. So simply speaking, what we observe is by simply increase the number of transformer blocks and secure a large enough data sets, we can immediately get improvement by training it using many, many GPUs. So this is called scale-up law, and this is still happening until today. But this requires enormous amount of GPUs. For example, the training of ChatGPT model with 170 billion models with dozens of billion words requires over dozens of thousands of GPU. Now each CPU costs actually around $100,000. You can see this is a very expensive game. It's actually over billions, several $1 billion a game. That's why a lot of IT giants company, including Google, Microsoft, Facebook, they all invest money to purchase GPU from NVIDIA. That's why NVIDIA's stock goes skyrockets. If you look at the stock price in the recent 5 years, because it's a very expensive game. Only those IT giants companies can play. The academic side is kind of silenced in this recent 10 years. It's called the industry is leading the entire development of this new generation of generative AI. But academic group researchers working on the other theoretical part, like the safety, the potential safety and the disparity of AI models, and trying to understand those models side. But the entire development is purely driven, almost purely driven by the industries like the OpenAI, Microsoft, and recent DeepSeek from China. So it's almost purely driven by the industry. And there's a reason on that, because it's a very expensive game with very promising, profitable futures. For example, by 2024, the market of generative AI has hit $137 billion. And the projection in 2032 is the market will hit $1 $1.3 trillion. So by investing several billion dollars to gain for the trillion dollars market, that's good. That's really good, very good business. That's why a lot of the people, including the most richest people, Elon Musk, is working in this domain. And President Trump just announced his AI project trying to invest $500 billion to build this infrastructure to compete with China on this, or other countries and EU on this artificial intelligence. So this is a current story happening in this artificial intelligence research. And this is the first section of my talk. In the next slides, first we go overview some of our models developed using a supercomputer at University of Florida. We are lucky because we have a very good alumni who graduated from University of Florida and co-founded NVIDIA with Jensen Huang. So NVIDIA donated us a lot of money, and with a supercomputer with 1,200 GPU. So we were able to do some large model training at University of Florida on the clinical domain. So this is the next section I'm going to talk. So the first model we developed called Gatortron. I mean, at University of Florida, everything is some kind of gators. Like we have Gator 1 card, we call our gators. So the model becomes Gatortron at University of Florida, which is a typical encoder-based model following the BERT architecture. The model is trained using over 10 years clinical text data collected at UF Health, which is over 82 billion words of clinical text. We added a lot of open source data from the biomedical literature, from PubMed, as well as some open and clinical data, which are able to bump up the size into over 90 billion words. And we trained the model using the HyperGator AI, which composed a lot of GPU. We end up only can use 992 GPUs on the HyperGator because of the overheating issue. We don't have those AC air conditioning, industry level air conditioning to cool down those GPUs. So eventually we are planning to use all of the GPUs, but the AC are not compatible to cool down those 1,200. So this is the maximum number we can use, 992 GPUs. We're able to complete the training in 6 days, which is impossible without this supercomputer. Without this computer, I think by the time I give this talk, this model is still in training. That's how critical the hardware resource is for the current models. For example, if without hundreds of thousands of GPU, in order to train the ChatGPT model with 175 billion parameters, it takes 36 years. 36 years. So maybe after when I reach 70s, I can finish the model. It's just not doable. That's why. But by investing billions of dollars, you can reduce the training time into several months, even several weeks. So this is how critical the hardware resource for AI competition now. So we released a model as open source. It's the mostly widely used clinical large language model in the medical domain. And the model has been downloaded over 1.5 million times. It's an old number. I think now we have more than that downloads now. It's pretty popular model in the clinical domain. And this model achieved good performance in terms of different clinical NLP tasks, recognize perform concepts, infer the entailment of sickness, and then perform QA questions. So this is pretty good model. We are not surprised because it's model pretty large than the BERT model. The model is up to 4 billion parameters, which is pretty large compared with the BERT large at $345 million. So it's just the replication will scale up a lot. By scaling up the data size, by scaling up the model size, you automatically get investment back. It's like fixed income investment. That's why the industry love it. It's invest money and you got push back revenue immediately. The second model we trained is called Gatortron GPT. Is the GPT models with a similar architecture with ChatGPT. The reason we trained the Gatortron model following the BERT first is we don't know which model works. We developed all the model before ChatGPT, and we don't know whether the BERT model works first or the decoder model works first. So we follow Google. I mean, you have to trust Google. It's a big company, and Google invests a lot of effort in the encoder-based model and encoder-decoder model like T5. But whereas OpenAI focus on the decoder branch using the decoder transformer models. So we follow Google at the beginning, and because all the model is developed before the ChatGPT. And if we know the decoder model will work at the end, we definitely try the GPT model first. But since all the model developed before that one, so we start from the Google's preference, the BERT model, encoder-based model. And then we shift to the generative model because that was an amazing performance ability of generative model, which it can generate clinical text. So we bumped the model size, the data set from 90 million to over 270 million. So we were able to bump the model size. You can't train large model without enough data because the model will be underfitted if the data set is too small. Those current models are trained using trillions, thousands of trillions parameters. It's even larger, way much larger than we trained this Geratron GPT model. But so we were only able to bump up to 20 billion parameters. We don't have more data. Certainly, we can train over 170 billion parameters, but we don't have more data. So the problem for us is we already exhausted all the text data here at one institution. So after we have model, we train the model. We applied one model to solve all different NLP tasks we solved in the previous Geratron paper, where we use fine-tuning. So we actually have applied 7 different models, but now we only using one model to solve all the tasks. As a generative model, what we do is we apply this model to generate a lot of synthetic text. They are not true, but reads like real notes. So we call synthetic text. And then we train a synthetic model using the synthetic text. Basically, we borrowed from the Google's idea. Google developed this ARPA-0 to beat human champion in the game AlphaGo using human played records. Eventually, they developed ALPHA-0 without using any human player data that can beat human champions. Similar idea, we try to using pure synthetic data, develop a pure synthetic model. We want to develop a pure synthetic clinical large model that can outperform real-world model trained using clinical data. We also perform the Turing test using 2 physicians. We asked 2 physicians to look at those sections written by Geratron GPT and sections written by human doctors from your health. We try to see whether they can differentiate from each other. So this is a study to them. So the synthetic model is quite promising. It turned out to be those synthetic model performs comparable to Geratron, even using smaller number of data. Sometimes it's better than the Geratron model trained using real-world data. This is a table report. You can see the at least comparable to the real-world Geratron model by using a small number of data, like 5 billion. So our observation is by using 5 billion synthetic data, it's almost comparable with the Geratron model trained using 90 billion words of data. And the reason is the AI model use many more diverse vocabulary than humans. Humans have a very narrow vocabulary. Like for each human, they only used to use thousands of words. But for AI, they actually can use much more diverse vocabulary. For example, the Geratron actually have 10 times much vocabulary than the real-world nodes. In terms of bigrams, the Geratron model can generate over 8 times more bigrams than the real-world patients. So in other words, the machine are more diverse than humans. So using smaller sample of data from machine, we can get equivalent models. This is very interesting finding, which indicate in the future we'll be able to develop a pure synthetic model without any human data. And the Turing test is also very interesting. It's not here. The Turing test is very interesting. By the statistical test, we can see that there is no significance between the Geratron GPT generated text and UF Health written text, which means that even the physicians cannot differentiate the text written by AI and text by physicians. In fact, the paragraph written by AI looks more like human than the sum of the notes because the paragraph style of the notes. So this is an example of the 2 paragraphs. One is written by human physicians. The other one is written by Geratron GPT is very close to each other. And a lot of the notes from physicians are really very hard to read compared with the notes written by AI. This is very interesting findings. All right, so these are the 2 models we developed. So when we have the models, we apply the model to a bunch of applications at UF Health to solve a lot of clinical NLP, medical discovery, and healthcare problem. So in the next 3rd section, I'm going to quickly go over some of our projects applications to show how we use AI to improve our data infrastructure, medical discovery, and healthcare efficiency. So the first project we conducted is called Computable Consortium Determined Health. social determinant health on a lot of non-medical relevant risk factors are highly associated with a lot of disease risk factors. Up to 80% of healthcare costs actually linked with social determinant health. It's important to identify those people who have disadvantages, non-medical risk factors, and target the population to improve their health. But most of this behavioral information and social information, like the income and their employment, is not well structured in the notes. So we under the support of PCORI, we started to project to develop NLP system to extract social determinant health and then to support the data element extraction at our clinical development house. So we try to examine, can we using the social determinant health network infrastructure like OneFlorida to help health outcome studies. And the goal is to fill the gap of using social determinant health for research. I mean, if you look at some of health outcomes, for example, premature deaths, only 10% risk factors in the healthcare system. 30% from genetics, 40% as on behavior, 20% on social, and 5% on environmental. So only using clinical data from healthcare is not enough to assess the risk of premature death. So we want to solve this data gap. Without this, as student from clinical text, you will have misinformation in the model, which caused unbiased factors causing either misclassification of machine learning models or confounding issue for static models. This is a huge challenge for the computational approach, either for machine learning model or statistics model. And there's a very diverse SDG category. And by summarizing different results from Health People 2030 and World WHO and different NIH centers, you can see there's much more diverse categories, including 7 big categories, 38 different subcategories. We developed a corpus starting from cancer patients because we know that the cancer center, our cancer center requires nursing investigator to ask the patients their social determinant health, like the employment, their behaviors, then to determine the best treatment plan for cancer. So we know they are going to document some research. The documentation is very diverse. Some of them are pure narrative. Some of them are semi-structured. Some of them are multi-choice questions. Diversity questions. Then there was a lot of different answers. You can pick up the one mark with the big X. Quite complex. And we performed annotation and trained our Gilroy model to solve this task. We developed a system that can extract social determinant health at a very good accuracy over 0.93% FS4. But once we found that by annotate 600 nodes, we only able to identify 19 category of 38 SDHs. And the documentation show is quite different from different visual group of patients. For example, we found that some of the category are very highly documented for the Black group. For example, the abuse, transportation, financial constraints categories are very high compared with other categories, if you like Black. And this actually reflected, previous study reported that the Black people are more likely to suffer from these advanced advantages, which means the EHR data, SDH documented EHR data actually can reflect real world, some of the real world disparity in healthcare. And we conduct a study trying to examine whether we can use the NLP extract SDH to replicate some of the well-known social determinant health. For example, it's well known that physical activity, marital status is related with breast cancer survival, but it's not able to quantify them because it's not well structured. We actually conduct a study to evaluate what's the association between NLP extract SDH versus the cancer survival for breast cancer. We were able to replicate those well-known protective SDH, active physical activity, and marital status, divorce, and single is associated with a bad outcome for survival outcome for breast cancer. The SDH also associated with pharmaceutical outcome. In this study, collaboration with our pharmaceutical researcher, we were able to replicate unmarried, unemployed, housing insecurity, current smoke and drug use is highly associated with the low use of a specific medication, which have a lower risk of toxicity, but the use rate is very low compared with another drug with higher toxicity because of this patient population suffers more from the social risk factors. So this study shows that the NLP extract SDH is really useful. We can use that to quantify the SDH category versus different health outcome to enable the study of SDH using electronic health records. But when we applied this model to a participating site in the study, in the PCORI study, we found a problem for using the models. First, when we applied the model at Cornell, we observed the performance drop. Some of the categories dropped sharply. For example, for occupation, drops sharply from 90% to 75% because of the New York's metropolitan area. Their occupations are quite different from Florida, where we have a lot of rural jobs, and New York has a lot of white collar jobs, so those categories dropped a lot. So in the next phase, we are working with PCORI again to develop the NLP model with good generative abilities using transfer learning, which is why very unique ability from those large language models to make sure the model not only works good at UF, but also works at New York as well. So this is the extension of these previous projects. When we apply the model to different study, we observe some of the limitation of generative model too. For example, in this study, we examined GPT to solve 7 different clinical NLP tasks just using one model, using prompting. It's achieved state-of-the-art on 5 out of 7 tasks. It's pretty good, but there was a huge problem there. There is a hallucination risk, which is not existing in previous models based on classification, where the category is predefined. But it's very hard to control the generative models because sometimes it just not follow human instruction. For example, when we ask the model to generate drug dose relation, the model sometimes just hallucinates with nonsense words, like the previous 2 examples. Those are totally hallucination without any meaning. And sometimes the model just started telling their own stories. For example, we're trying to identify the dose information for a medication. The model started to explain what is that medication. It's not what we wanted. So this is called hallucination, which is the key bottleneck of applying generative AI to healthcare. If you cannot solve the hallucination and control the potential risk to patients, it's impossible to move the model to the consumer side. So this is a huge challenge. So we have some algorithm to trying to solve this issue to control the hallucination risk. This is a one-off study trying to solve this issue by degrading the model. The pure generative model is free text generation, free text QA. The model has no limitation to answer questions. So in our solution, we try something. We, typically speaking, we remove the free text speech away from the model. We force the large model to answer the question only using the text from the original claim notes. On one side, yes, the model is limited. They can't use other words. They lost freedom of speech. But on the other side, you can fully control the hallucination because you won't have words out of the vocabulary of the claim notes. It controls the problem well, but it only applies for some of the tasks. For example, summarization, where you have the original text to consolidate, but for free text, answer question still you can't fully solve using this model. Another challenge for using large model is prompt engineering. Probably if you use ChatGPT, you have to try a lot of different ways to ask similar question because there is no way to instruct people how to write a good prompt. It's purely experience driven. Sometimes we only change a little bit of prompts, the model changes a lot because the current prompting strategy is still not mature. So in this study, we tried a different solution. Instead of human instruct large language model, we train a AI as delegate of humans. We ask human to label some of the question and answers. We use that one to train this AI to ask large language model. And our result is quite promising. It showed that the AI is currently better than human in terms of communicating with another AI because human cannot enumerate all the potential ways asking, but AI can, right? AI can enumerate 1,000 times, millions of times just in very short time, which is human cannot. So this is very promising, indicating that we can use the AI to learn how to ask a larger model, then use AI as a delegate of human to control another AI. It performs way much better than human to control the AI. And this is a paper we exploring this algorithm. And when you use the frozen LM versus the advanced tuning, we observed increase on the future learning abilities, which is quite promising. for large language models. And with all the language models and all the solutions solving those bottlenecks in terms of rate, potential hallucination, and tuning algorithm to handle those come up efficient prompts, we were able to solve different NLP tasks. I'm going to go over some of the use cases. All of them is solved, but it's only using one model, the Giltron model. And also in University of Florida, we actually deployed a lot of our AI modules, not only as research, but also as an infrastructure. We build AI infrastructure at UF Health. We deploy our foundation models into our clinical data warehouse, into UF Health, and clinical care flows also across 27 million patients from the OneFlorida Plus clinical research network. In terms of NLP infrastructure, those ones highlighted have been deployed at clinical data warehouse, and we are implementing those ones on the list. So the UF researchers don't need even use language model to extract data. They just query from our clinical data warehouse. They can utilize our social genomic health, quantitative smoking, the cancer nodule, different characteristics and appeal builds flags directly querying from the database, which greatly improved efficiency for their research. We're providing services for researchers from the UF Health, focusing on computable phenotyping, information extraction, different data elements, predict modeling based on reasoning over language models, which is quite different from previous generation of decision model based on classification-based models. We provide support using generative AI-based reasoning models for predictive disease risks and decision support. Also, we're doing a lot of tasks trying to reduce the clinicians' burdens by developing summarization, trial matching different algorithms. And by developing not only research problem, but also AI infrastructure, we were able to support a lot of research, like in University of Florida, the NLP core is supporting almost 20 different R1s from different agency going. So it's pretty large impact from the NLP core at the CTSI. And I'm going to use the rest of the time to go over some of the AI infrastructure and applications to show how we use AI to improve infrastructure support the research. And the first infrastructure we developed right after I moved to University of Florida is the de-identification system. It's a foundation for generated totally de-identified, not totally, somewhat de-identified copy of clinical notes for research to reduce the potential sensitivity from healthcare institutions to use clinical tests for research. So this
Professor,
is developed,
can you slow down a little bit?
Oh,
Hi, can you slow down just a little bit? I didn't catch that last thing.
I mean the speed of the speech, all right? Hello, can you
I think maybe just repeat the last thought and
the
ask
question
the ask
to-
was to slow down just a little bit. Thank you.
All right, great. Let's go back to the one. So this slide is simply showing by developing AI infrastructure, we are able to just putting AI module into any outcomes research, focus on different disease domains across different college to support over 20 ongoing external funding from different funding agencies. Right. So this is the first thing we developed at UF as part of the CTSI infrastructure, which is the DNA copy of clinical notes. Using Giltron, you have different copy of models. With the help of Giltron, we were able to remove 99.7% of p-chat from the notes to create almost DNA copy of clinical notes for research. And we accidentally killed about 3% of non-p-chat text, but our ARBs really like a system with a high recall. But if we accidentally remove non-p-chat text, they are pretty good with that. So that's why we really developed this very high recall system. Even though it accidentally killed 3% text, it's still good for the research purpose. So this is a first infrastructure we developed supporting the CTSI de-identification effort. And this is a collaboration with our cancer center, and we have a NCI Genetic Cancer Center, which a lot of information are kept, the nodule information, the size, laterality, the tumor information, also a lot of biomarkers. They were captured, but not structured, not able to use for research. in collaboration with Cancer Informatics, we developed this tool to extract different tumor information, nodule information, and biomarker to structure them into the database to support cancer research. And this is another opioid research supported by ongoing R1 from NIDA. We trying to develop an NLP tool to detect potential overdose of opioid, so the doctors can intervene those patients with high risk. And we developed this system using different categories of overdose and symptoms like the urine test to revive the medications and combine this information with structured history information of patients to predict the risk of overdose of opioid, and which is deploying at our Epic system, and we have recruited a group of physicians to test the system as a pilot test. Medication change and PCORI is also very interesting because in a lot of diseases like opioid and mental health disease, the patients frequently change their medication a lot. So we try to detect the changes of medication, including the start, the change of the dose, and stop of medication, and we try to understand what's the reason causing that medication change. And we try to build an AI model that can better triage the treatment pathway to identify the shorter treatment pathway for specific patients to reduce their pathway to looking for treatments. And adverse drug events is also a very good application. I mean, a lot of medications still have adverse events even after the 3 phase trials. We were able to use clinical notes to identify the mention of adverse events and identify which medication caused that adverse event, use it for pharmacovigilance study. And collaborating with our aging ADRC center here, we developed an NLP system to extract different cognitive scores, as well as some of the well-known genomic markers indicating high risk of Alzheimer's disease. We also developed these computable phenotypes to identify either healthy aging population or high-risk aging population to recruitment patient to enroll patients into the clinical trials. Those are very good information to using eTrial to simulate trials, because those cognitive test scores are very used a lot by the trials as a measure in the trials a lot. So this will enable the use of electronic health records to simulate a lot of aging-related trials using these cognitive scores and biomarkers. This is a study leading by one of my PhD students. We trying to advance the current decision support. Instead of using the traditional machine learning-based algorithms based on the classification models like XGBoost, slot vector machines, we apply our regression model to reasoning over narrative text instead of classification using 0 and 1 features. And the results is very promising, which shows the gauge perform pretty good by identifying heart failure in cancer patients, which is quite challenging for traditional machine model using those structured data. We actually can do much better by using reasoning over narrative features. This is another of my PhD students, Meng Xian, is leading this project. We're trying to develop a summarization system, automatic summarization system to summarize the patient and the physician's encounter into clinical sections. And the performance using Gauge GPT is pretty good compared with general domain models, which is showing the training using clinical model using clinical data is quite promising compared with general models. And there's already very mature product in the market, for example, DEX from Nuance. We are implementing that one at U of Health. And there's a lot of institutions implementing the DEX too, which greatly reduced the clinician burden. And Meng Xian is also leading another project, and we're trying to use Gauge GPT to solve this treatment plan generation problem. This model can automatically summarize structured and unstructured data from patients into a very short, concise patient profile. And then we can use our model to reasoning over the profile and generate the corresponding treatment plan following the treatment guidelines from the NCCN guidelines, which is a typical RAG system. The promise is still very good after we collaborate with a lot of oncologists to train the models, but you need oncologists involved to instruct model how to generate treatment plans. And this is a model we developed to help physicians to recruit patients from
using electronic health record. At the RC, we are running a lot of trials to enroll a lot of aging populations, but one critical effort is the physician has to review hundreds of patients to recruit them into the trials. In this system, we applied our Gittertron to first understand the inclusion-exclusion criteria of trials, and then we're using that criteria to matching patients using electronic health records, using a typical question answering pipeline, which is very natural QA solution for trial matching. And evaluate using a complete trial focused on Alzheimer's disease, the promise is pretty good. We can solve 86% of the criteria by recruiting the patients and using electronic health records. This is an ongoing project we just received from ARPA-H, focusing on using multi-model solution to improve rural health. The problem for rural health is there is a shortage in terms of healthcare providers, physicians, even including the technicians. So it's very hard to perform some of the very basic lab tests to enjoy the telehealth. So in this national projects, we are collaborating with a lot of researchers to develop mobile units that can be delivered to the rural area. And we are going to develop a multi-instruction system that are able to instruct normal people to do some basic lab tests like the CT, EKG, those lab tests. Then they can transfer the data, those lab test results back to physicians to enjoy the benefit from telehealth to improve the rural health. This is another project I'm leading that we're trying to use electronic health records to identify the new uses of existing drugs, which is known as drug repurposing. Basically, we are using machine learning model trying to tell us, okay, this is one drug on the market. This is used to treat another disease. Do you think this drug have potential treatment signal for Alzheimer's? So this is the typical classification or task based on traditional models. But recently, there's a surge of using generative AI for drug discovery. And you can take a look at these applications. What happens is, by using generative model, the previous generative model only can perform classification tasks. Human have to give them a drug. This is the drug. This is structure. The machine can tell you if the structure may have some potential treatment. But in the future, when the generative model become mature, what we can do is we can ask the generative AI to generate a new molecular or protein or chemical structure with desired functions. It's very promising. Some of the articles from Stanford group showing very promising. For example, one of the studies showing that they can ask AI to design a protein structure never exist, but really have a function to anti a specific virus. Those are very interesting. This will greatly speed up the drug development by using generative AI. So in the future, you can do some funny stuff. You can ask AI to generate some medication with a specific information. If the technique becomes mature, the AI will be able to generate some instance not even exist on the world to speed up drug discovery. So to sum up, the large language model really opens a door of generative AI, but there's a huge challenge to move this technology really to healthcare, to patient health. There is a huge challenge, but if it's successful, that will be a huge impact to the healthcare system. For example, I already mentioned the hallucination issue. How to ensure the safety of the model, right? If the model doesn't follow instruction, you can easily ask the model to tell your social security numbers. So this is a potential safety issue. And the prompting is not mature, as I talked. And the real bottleneck is the current model is not always good. Big is not always better. For example, we can easily develop a local model, performs way much better than large models on one specific task. The large model only good at solve thousands of models in one model, thousands of different tasks in one model. But if you look at one specific time, it's not as good as the developed model, locally trained models. This is still the case. Even though the model only achieved 50%, people will be amazed, but it's not applicable to the real world medical application. The big problem is data exhaustion. By now, we already exhausted all the data in the world, in this planet. It's just dozens of trillions of words. We already exhaust all of them.
to keep the scalable law going, we have to find a solution. And my solution is text generation. We can ask AI to talk with AI. We can easily enumerate all the combination of language to solve this data exhaustion. And in the future, my goal is to develop a pure models out of any human data. And to end up, I would like to mention about the Nobel Prize last year. We probably heard a lot. AI won 2 Nobel Prize last year, one for physics by the invention in artificial intelligence. The second one in chemistry by solving the protein structure prediction, which typically takes half a century to solve. But now with AI, we can solve it in 2 years, and which caused a crisis in the job market as well. So last, I would like to acknowledge my collaborators from my department, from different UF entities. College of Medicine Research Computing Research Community team is the critical support to running almost 1,000 GPUs. It's impossible. By running 1,000 GPUs, you get a lot of hardware issues that could happen during the training. You have to plug in, plug out those GPUs a lot. Also, we collaborated with a lot with NVIDIA. This supercomputer is donated for free by NVIDIA. Also, my collaborators from Cornell, Yale, Penn, Pittsburgh, and Mayo Clinic. This is the supercomputer we have at University of Florida. It's pretty beautiful. So I would like to stop here, and time is pretty good. I have 9 minutes to answer questions if you have, Sarah.
Great. Thank you very much, Dr. Wu. That was a really interesting talk. We have one question on the chat, which I'll read out for you. And then if anybody else has any other questions, feel free either to speak up or to post on the chat. So this question is from Florent. He says, thank you for this very comprehensive and interesting presentation. 2 questions, it seems. Number 1, for medical knowledge, have you compared fine-tuning on clinical data versus using some RAG strategies, or a balance between the 2 approaches would be best? And 2, regarding distributed infrastructure, what would be the feasibility of a system based on some blockchain framework?
All right, first is a very good question. For the first question, RAG, the comparison between fine-tuning and RAG is really related with the target application. Both for some prediction-based tasks like the classification tasks, the fine-tuning, there's no big difference between fine-tuning and RAG. The real difference is on whether you need some generative AI, for example, answer questions or generate narrative phrase. In that phase, there is a difference between the 2 strategies. But what we observed is we can combine them together in one application. For example, in the treatment plan generation, the entire model is tuned using clinical text. But when you generate treatment plan, we're using RAG to incorporate the clinical guidelines into generation. This way you can combine RAG and the larger model fine-tuning together in one model. It works pretty good. For the second question, blockchain frame. This is, I need to double check. I don't have experience using blockchain on the work. As far as I know, there is no blockchain involved in the large models. So yeah, this is a good question. I need to double check, and probably we can talk later.
Great, thank you. I think Young has his hand up, so feel free to unmute yourself here.
Thank you, Dr. Wu, for the great talk. I had a question regarding model size and sort of downstream inference. You mentioned that Gator Trial has several different parameter counts that we can choose different smaller versus large models, even within the same architecture family. My question is sort of, given that there are trade-offs between inference, especially in sort of low compute settings, like you said, in sort of rural settings versus higher performance or possibly higher risk of hallucination with larger models, how you would sort of balance that trade-off between inference costs and downstream performance?
All right, this is a very good question. The question is about how we balance the model size, training costs, and the real-world application. So the strategy, I'm consulting a lot by other people how to use AI, but my suggestion always, if you can solve the problem using the smallest model, using the simplest solution, go for it. I mean, there is a lot of application in the clinical domain. We don't need large models. For example, we only need the model tell us whether the patient have a tumor, right? We don't need the model to amuse you, tell you a joke, or answer who is the beautiful woman in the world, right? Those are not specific for medical applications. I mean, for general AI, like the OpenAI trying to achieve artificial general intelligence, yes, they have to consider about this. But for a lot of medical applications, as far as I know, there is very limited space we need generative AI. For example, the only application I think involve generative AI is summarization, right? You have to perform the document level. You have to perform document level, some multi-document summarizing, or patient encounter, like the DEX. But even for the DEX, it's not pure generation. It's more like a voice to text translation. And then you just classify whether the text is medical relevant or not. So there's very limited application of generative AI in the clinical setting. And one problem is they still cannot control the potential hallucination risk. Without control that, they cannot bring that to the consumer. So if you look at the current generative AI application, most of them is on the provider side. It's help the doctors, help the nurses. It's never reach the patients. So there's a huge space how to control the risk, how to train those healthcare providers, how to conduct AI intervention trials to prove that the AI model really works. So there's a huge space there.
Thank you.
Super, thank you. Are there any other questions? I have one myself, but in the interest of fairness, I'll wait to see if anybody else has one. Okay, I can ask mine. So first of all, again, thank you, Dr. Wu, for the presentation. I guess I wanted to you guys had produced Gator and you spoke in detail about that. I guess I wanted to know what your thoughts are moving forward between like using one of these sort of large general purpose models and fine-tuning it for a medical purpose versus from the beginning building a smaller but dedicated model that you've done with Gator. Do you foresee in the future that the better option is to go with, say, just kind of like fine-tuning a large model like OpenAI's, or do you think there's still benefit to continuing to train specific models?
It's a very good question. So the reason we developed Gatortron is by the time 2019, there are not much large models available in the NLP domain. The large one we have is BERT. So we trained from scratch using our own data, using the supercomputer. We happen to have data and happen to have donation from NVIDIA, so we decided to do something. But at this time, I would recommend you to start from some open source model like Llama is really good. And for a lot of the applications like classification, information extraction, if you fine tune the Llama model, it performs actually comparable with Gatortron. The only one Gatortron GPT actually works pretty good is written notes. If you fine tune Llama or even ChatGPT, their written is very generic, not clinical enough. We did some experiments comparing Gatortron GPT and ChatGPT and other Llama to general note. They are very too generic. They're not even real past the Turing test. So this is the only application that Gatortron GPT is still good by writing the very genuine clinical notes.